So my name is Manabendra and today I am going to talk about the path integral methods in quantum mechanics. So here's the title. So normally in quantum mechanics we know basically in the Hilbert space formulation what you have is states and observables. Where your states are elements in Hilbert space. By elements, I mean vector elements. And observables are basically operators acting on this Hilbert space. Acting on is vectors sitting in a Hilbert space. Okay, and the dynamics is given by the Schrödinger equation or equivalently we can say psi t is I h, where h is the Hamiltonian, t naught is some reference time, and so all it says is if you know the state, I'm using Dirac bracket notation. So all it says is if you know the state at time t is equal to t naught, at any later time t, it can be computed using this relation, which is nothing but the Schrödinger equation, which is t psi t so where I'm taking h cap, setting h cap to be 1, so these two are equivalent. All right. So this is the method we follow in the Hilbert space formulation, but today we are going to talk about path integral methods. I'll quickly review the classical situations. So in a classical picture, what you have is a action so which is an integral of the Lagrangian. It's a function of generalized coordinates and generalized velocities. All right, and the extremum of this action gives the trajectory So if I draw it, so what you have is q is the coordinate and t is the time. So from some ti to tf, if you want to know the correct path, that is given by this least action principle. Classically, this is classical. Okay. But quantum mechanically, it could be possible that all paths, the probability of going a particle from all the paths has to be taken into account to know the transition amplitude. If you want to know the transition amplitude or the probability of for the particle, for a one particle system, the probability for the particle to go from qi ti at ti to qf at tf will be sum of all the probability amplitude. Will be the sum of the contribution from all the parts. So that is the basic idea. So, and today we are going to find the matrix element, metric element basically. So what we are going to find is this qf at some tf given qi ti. So we are going to compute this matrix element. All right. So, few quick definitions. So Q I write as in a condensed notation. Q alpha denote collectively the coordinate degrees of freedom. Collectively the coordinate degrees of freedom. Let Q get Q are the simultaneous eigenfunction of the position operator Q alpha such that we have Q alpha acting on Q on the Q state gives us Q alpha Q for all alpha is equal to 1 to n. Therefore, the state of the system in positional representation psi qt is q psi t. Of course, this will lead us to psi q prime t prime psi at q sometime t q prime will be q prime psi t. I'm just using this definition, which will be equal to q prime e to the power minus I h t minus t naught psi t naught. Which is nothing but q prime e to the power minus I h t minus t naught. What I'm going to do is here introduce the identity operator. I can always write like this, where this product, when I integrate it over, will give me the identity operator here. So that doesn't make any difference. So that is equal to T naught. So what we have here is dq q prime h t minus t naught. So is q, and that will be psi q comma t. So this guy sitting here is called the green function, which we write q prime t prime q t defined as q prime e to the power minus I h t prime minus t q. So this is the green function or the propagator, and it is defined in this way. So in this very short lecture, I'm going to give some hints. Because of the time constraint, I cannot complete the full derivation, but I'm going to give the hint how to proceed to calculate this quantity, this matrix element, and I'll state the results at the last. So let us now note one important property. Property of this green function of this green function z, which says z q prime t prime q t is equal to d q double prime z q prime d prime q double prime d double prime z q double prime d double prime q comma t. All right, this is one of the important property that led Feynman to have build the path integral representation. Okay, so now I go on to calculate this quantity, which is q prime, t prime, t prime, and qt, which is equal to q prime e to the power minus I h t prime minus t q. Okay, so what I do here, so I have this state called energy state, okay, which is complete basis for the energy eigenfunctions. So in the operator, then I have q, but also for the position and for the momentum as well. So let's say this is alpha, then alpha is I. So with this in mind, what I can do is insert these identities in between. If I do it and I do a transformation, that is t going from minus I tau and t prime going to minus I tau, the importance of this transformation is apparent when you do quantum field theory, because it makes the field theory Euclidean. Okay, that I may talk about in my next lecture. So to arrive at the path integral, I am giving the procedure. So what we do is we divide this time interval tau prime to tau into n dimensional segments of length epsilon tau prime minus t by n. So we divide, what you do is divide this into n dimensional n steps, each of which epsilon, which is given by the total time divided by the number of steps. So basically we are discretizing the path, and with this, and if you assume your Hamiltonian to be of the form half alpha 1 2 and p alpha squared plus pq, if you assume the Hamiltonian structure of the Hamiltonian would be to be of this form, will end up with we'll end up with, I have to rub this. We'll end up with, I'm giving the final result because of the constraint in time. Q L plus 1 e to the power minus h epsilon Q L is approximately e to the power minus epsilon v q L integration. For that, beta is the 1 to n dp beta L by twice pi alpha is the 1 to n exponential minus epsilon half p alpha L whole square minus I P L alpha Q L plus 1 minus Q alpha L divided by epsilon okay. I closed the bracket already. So with this we have, what we have is L prime. If you calculate the matrix element e to the power minus h tau minus tau Q, the final matrix element, what n minus 1 alpha 1 to n dq alpha L prime root over 2 pi epsilon. So e to the power minus L minus L equals 0 to minus 1 epsilon LE is a function of QL dot and QL dot. All right. So this is my final expression for the matrix element I wanted to achieve. Of course, I'm missing many steps in between because of the time constraints, and the L is the Lagrangian and written in the Euclidean time. Therefore, this is as a subscript here. So this is a function of QL Q dot L alpha half Q alpha L dot square plus V Q L. So I have introduced, of course missing many steps in between, but giving the important procedural steps to finally get the matrix element for the particle to go from the Q state to Q prime state, which is given by this. So thank you very much.